Okay, YouTube, in this video we're going to look at a special classification of polar equation that is of this form: r equals a plus or minus some b times either cosine of theta or sine of theta. But essentially what we get are graphs that we refer to as limacons. Okay, so all of these shapes that you see over here are limacons. And limacon, sorry about that. But this is kind of a shape scheme here, and you can see kind of the evolution of a limacon here. It can kind of change its shape. But what we hope to do in this video is basically kind of describe some key characteristics of the graphs, as well as the effects of a and b upon the graph, and maybe even cosine or sine. Okay, so what I've done is actually I've created this general limacon here, r equals a plus, I went with a plus here, b cosine theta, but you see that we get our limacon here. I just want to kind of share with everybody here that if we change the value of, say, a here, how a compares to b, you can see how it has this loop in the middle. And as you fold that loop out right there, you get a cusp. Oh, see that looped back in right there. We get a cusp right here, so we get a heart-shaped thing. Okay, and as we fold out even more, we would say that that heart-shaped thing after that cusp right there becomes like a what we call a dimple right here, and then eventually we get what we call a convex shape. Okay, so what we're going to say here in this video, at least, is we're going to share out some simple things about these. We're going to refer to this first one right here as a loop. There's a loop in it. Okay, this one right here we're going to call cardioid. Cardioid. If you're in med terms, you say heart-shaped, cardioid, okay? We also call this one, like I mentioned it here, is it called a dimpled limacon. And then this right here, we kind of got a bend right here on the left side, but this is what we would refer to as a convex limacon, okay? So this is kind of the evolution right here, and what we're going to remember is basically a mnemonic, and I cannot take credit for this. I can't. I got this from somebody else's notes, but we refer to a mnemonic here to help us remember this. Lou loves dimpled, and they wrote cuties. And I don't know if they're referring to those little oranges or what, but I kind of think of it this way. We say Lou loves dimpled cuties. Lou kind of refers to loop, okay? Where loves, we say loves because of this heart shaped here, so a cardioid, all right? Dimpled, well, just dimpled. And then cuties, I kind of think of those little orange things. It kind of looks like a cutie with a little dimple on the top here. So that's going to kind of help us remember here that cuties goes with convex, and then loves is heart shaped, so cardioid, loop, and then dimpled is dimpled, okay? So here's what we're going to do. We're going to go through this, and we're going to, look at these shapes of these graphs, starting with what effect does sine and cosine have on this. And I guess I want to kind of point out something here that is already something we should know, but if it's cosine graph, then it has symmetry with respect to the polar axis, or the positive x-axis, or just the x-axis. So if this is a cosine thing, it doesn't matter, what we have here. We're going to have something that is symmetrical with respect to the x-axis. You can see a limacon there. So we say that if I were to make this a sine graph, it would be symmetrical with respect to the vertical axis, and we can see how that would kind of affect that here. Okay. So the first thing we want to note here is that sine and cosine help us determine symmetry, and I'm also going to say sort of direction, okay, and direction. And the reason why is because if we have a limacon, that is cosine, we're going to find out here this plus or minus in front here. What if we make b positive or b negative? Let's go try this out. If I make b positive here, and this is the coefficient of our trig function here, essentially what we see is that that b being positive there causes the sine graphs to open upward, but if it was negative, it causes it to open downward. And the same thing is going to happen if we were to go back and make this a cosine graph here, b cosine theta. It would open to the right if b is positive, and open to the left as b is negative. But we still have that x-axis symmetry there. So we say plus or minus. What we're going to write here is basically plus or minus is going to determine, if I can get my pen to work. Oh, wrong side of the pen. So let me zoom out here. All right, thanks for being patient with me. Plus or minus on our b value here basically opens, or direction it opens. Direction it opens. Loosely saying that it opens, okay? So a plus b, here's one thing that's really interesting about this. But we say a plus b, what effect does this have on our graph? And what I want everybody to notice here is currently, let's get some nice values. What if a were equal to 1, b is 3? We get this limacon right here. But if we said a plus b, I would get 4. And if I did a minus b, I would get 2. But what I want everybody to see here is that 4 right there is directly indicating what our maximum value of r will obtain. And if we were to do, like a minus b here, or b minus a rather, but the difference between these two is 2, you can see that this is our inner loop distance here. But basically, in general, we're going to say a plus b. What do we want to say about a plus b? A plus b determines the maximum r value. And we're always going to look at, when we say the max R value. We're always going to look at just these numbers as being positive. So 2 plus 3 would be 5. We're going to reach a maximum output of 5. And then A over B determines. Okay, so now this is the interesting thing about it. A over B determines the type of limacon. When I say type, I really am referring to these over here. So we're always going to remember it in this order. Lou loves dimpled cuties, or loop, cardioid, dimpled, convex. And what you want to write on your paper is basically how A compares to B. Now again, we're saying assume A and B positive. Assume A and B are positive. If that is the case, then if we do A over B and we say that this is less than 1, then we are describing something that will give us a loop, okay? If A over B is equal to 1, then we are describing something that gives us a cardioid or heart-shaped thing. If A over B is bigger than 1, okay, but less than 2, okay, let's put it that way. I suppose I should write it that way. It's bigger than 1 but less than 2. Then we get something that is dimpled here. And then if it just goes beyond 2, it kind of goes in this order here. Beyond or greater than or equal to 2 essentially. What we're going to get is we're going to get a convex thing here. So using the scheme, okay, using the scheme, I want to kind of make some general statements here. But essentially, if we were to have something like this, let's try this on for size. What if we had A plus B cosine theta? We would know we have something that is symmetrical with respect to the x-axis, and we would say that if I had A plus B, assuming that B is a positive thing, and I suppose we could say, I guess, let's see here. Yeah, B is a positive thing. We would say that this would open to the right, okay? If I said A minus B cosine theta, assuming B is some positive thing, but we're taking it away, so we have a negative in front of it here, we would say that this would open to the left. Now, if we were to say A plus B sine theta, because our B value is positive, we would say that this would open up, and if we had A minus B sine of theta, then we would have something that opens downward, okay? So that's kind of really good thing to refer to. So using all of what we've got right here, we're going to throw together some limacon graphs here. I'm going to do a few examples, but just this next one in this video. But we're going to put this together and see what we can find out about this. I think that it's helpful when you have a limacon to write out what A and B are equal to. So we have A is 2, B is 3, positive by default. We say, what shape is this going to make? So the first thing we want to do is this. We want to type this. We want to say A over B is 2 over 3. And what I notice here is that 2 over 3 is less than 1. So that was our first option here, or loop. So we have a limacon, and we have a loop is what we would put as the type, okay? So the maximum R value we said would be obtained as A plus B. So we say A plus B, which is 2 plus 3, which is going to be 5. It's going to go out 5 at most. And then in terms of number of zeros here, what we're going to do is we're going to solve for these zeros. So we would say, okay, well, we would get 2 plus 3 cosine theta. If we were to solve for now theta, we would get negative 2 equals 3 cosine of theta. And we could say, okay, well, negative 2/3 is the cosine of theta. And I suppose we could solve for our zeros from here. You know, I would say is just kind of a general premise. If looking over here, we say a limacon. Let's just put it this way. How many zeros is it going to have? I noticed that it would be at 0 here, and then loop around and come back to 0 here, and then, you know, just kind of complete itself. So it would go around 0, hits 0 there, and then it hits a 0 here again at the pole. So we would say that it just has 2 zeros, okay? And we can see this on these graphs here. All right, so looking at this, we say, what are some convenient points? The nice thing about this is we say that the period of all of these graphs is 0 to 2 pi. This is going to be what we do, and neglect that, you know, or equal to here, but basically angles up to 2 pi. So when we put these in, we're going to put in angles, and I think that it's really just convenient to use our quadrant angles here. We'll always do this. So using these quadrant angles, we'd say this is 2 pi. If we plug these in, we're going to get some values here, but plugging in the first one here, we say r equals 2 plus 3 cosine of our input. We say, well, what is the cosine of 0? Using our unit circle here, we say the cosine value here is 1. So we say cosine of 0 is 1, we get 2 plus 3 times 1 is 5. And we would say, okay, so at pi halves, if we plugged in pi halves here, we'd say the cosine value there is 0. So we get 2 plus 3 times 0, which is 2. Here at pi, we'd say cosine of pi, well, cosine of pi down here is negative 1. So we get 2 plus 3 times negative 1, or 2 minus 3 is negative 1. And then at 3 pi halves down here, we obtain a cosine value here of 0 again, so we get 2. And then at 2 pi, we're going to be back here where it's at 1. So we say cosine of 2 pi is 1. Well, 2 plus 3 times 1 is 2 plus 3. And we get 5 again. So when we graph this, we're just going to plot all these points. We say in a 0 degree direction, we're going to walk out 1, 2, 3, 4, 5. So you'll notice here that it's a cosine thing, and it's certainly opening to the right. We say, okay, well, at 2 here, or sorry, at pi halves, we're at a height of 2. So this is going to be on our graph. At pi, in the pi direction, we're going to walk backwards 1. So we get this point right here. Okay, weird, but we get it. We say 3 pi halves facing downward here, we're going to walk out 2 units. So that is here. And then when we're at 2 pi, we're going to be back at 5. So using this right here and looking at our loop over here, we say, what would this look like? Okay, and what we know is it's going through here. It's got a couple of zeros. It's got to go through here. But we would get something that loops around. Okay, it's coming through here, would proceed through 0, loop around on itself, and then because of symmetry, the bottom half is going to look like this. So my limacons never look that good, but we say that this is our limacon in this particular instance here. So again, you know, we typed it, we found the maximum R value, the number of zeros by kind of typing it here, and then plugged in 0 through 2 pi going by pi halves, and then graphed our basic shape. Cheers.